Welcome back to the videos for chapters 10 and 11. This is the last video for chapter 11, and I'm going ahead and posting this a little bit later because I wanted you guys to work through that POGL on the polarity of molecules first. So the topic here is molecule polarity, and then I'll tell you a little story to hopefully help you make sense of the hybridization. Okay, so problems in the textbook that go with topic 58 are 47 through 52. I'll help you work through 48, 50, and 52, and you should also be able to answer questions like number 60 that are just about hybridization without getting into pi bonding and some of the other things that chapter 11 goes into. Okay. Slides 23 through 25 have this information in your chapter 10-11 PowerPoint, and you can look in Chapter 11, including sections 11.5 for some of this information. So the first thing we want to talk about is molecule polarity. So if you refer to the slide deck, it says a dipole moment is a separation of charge. So for one bond, there would be a dipole moment just determined by the electronegativity between the two atoms. So let's just say I had a black and a green atom. Okay, I could just determine for a given bond whether it's polar or not based on the electronegativity. Okay, for a molecule, you want to consider the overall dipole moment. So this is going to be determined by two things: the bonds that you have, whether they're polar, and how they're arranged. So let's say, for example, the bond between this black atom and the green atom is indeed a polar bond. Okay, now each one of these may be polar, but you'll notice that this is one of our base symmetries, our electron geometries. So this has everything spread out as evenly as it can in 3D space. So in this case, the way that these individual polar bonds are arranged in space about this central atom makes it so that it is a non-polar molecule. If you think of each of these as having a draw for electrons, pulling essentially electrons from this central atom, if you try to pull in all these directions simultaneously, it really doesn't generate any net pull effect. So if you want to think about like the vectors like they talk about in your textbook. In bold on slide 23, it says molecular structures are polar if there are polar bonds and they are not symmetrical. So if you have identical bonds, like in this particular case, and they have symmetry around the central atom, they cancel and the molecule is nonpolar. Now, the interesting thing is if it is a polar molecule, it's going to interact with electric fields, whereas nonpolar ones do not. A couple other ways that you might state this. So if you remember at the end of the POGL exercise, it said polar bonds are necessary for a polar molecule but not sufficient. Polar bonds can cancel each other due to symmetry, making it a nonpolar molecule. There must be polar bonds that cause an asymmetrical concentration of negative charge on one side or one area of the molecule. One of the ways that one of the groups put it in the Google forum after the POGL was, if it has a polar bond, the bonds need to be evenly distributed to make a non-polar molecule. Otherwise, having polar bonds would make it polar. You can also find this information on the little chapter handout here, right between the electronegativity table and the geometries table, very much like it's stated in the slide. And we'll go through a few examples. So just remember, you have to at least have polar bonds and they have to not be symmetrical around the central atom. Okay, so that's going to give us a polar molecule. The other thing that we want to talk about is, and this is from, I believe, 11.7, this is hybridization. So while we're not necessarily going to go into some of the pi and sigma bonding and things like that, you may want to read a little bit of 11.7 to understand just the hybridization. I want you to be able to identify, simply based on the number of groups, based on the basic electron geometry, what hybridization is required. So if you notice step 20, or slide 24 has the steps to determine the hybridization. So you draw the Lewis structure, you determine the number of electron groups, regions, or domains around the central atom using the Vesper theory. Then you're going to assign a hybridized orbital system based on that geometry. Okay, so we're going to have a little story here about cake, and hopefully that will kind of help you have a context to think about hybridization. Okay, so let's say that I have some little mixes that make the little individual microwave mugs of cake. Okay, and in my pantry I have to use them in this order. Maybe they're lined up based on expiration date or what have you, but I'm forced to use them in this order. So I have one that can make a mug of spice, 3 that can make mugs of pumpkin, and 5 that can make mugs of devil food. Okay, so I'm about to sit down and make myself a cup of cake, and I'm going to be using the spice mix cake, and then I get a text message. Oh, one of my friends is going to be dropping over in just a moment, and I think, well, how rude for me to sit and eat in front of her. If I make 2 cakes, though, one will be spice and one will be pumpkin, and that might be awkward, right? Trying to choose, who gets which one and whatever. I really want to have 2 mugs of cake that are equivalent, so that I can present it to my friend and have one for myself, and they'll be the same. So I really want 2 equivalent mugs of cake. So here's what I'm going to do. For the 2 of us that are going to be there, I'm actually, before I bake the batter, I'm going to make up the S spice and the P pumpkin, and I'm going to mix them together so I have a spice pumpkin cake batter, and then I'm going to pour it into the 2 mugs and cook it, and then we'll both have the same flavor. Okay? Oh no, wait. Then I got another text. A third friend is coming, or a third person is coming, a second friend is coming over. Now there's going to be 3 of us. And again, I want to be able to serve them a mug of cake. I mean, I'm just about to eat mine. It would be rude. We've got to make them the same. Okay? So I'm going to take the mixes for spice and 2 pumpkins, mix them up with the liquid or whatever I'm supposed to do, and then divide them evenly into the 3 mugs. And now we're all going to have an equivalent yummy, warm little mug of spice pumpkin cake. Okay, so for short, for the 3 of us, I'm going to say SP2, because I've taken 1 of those spice mixes and 2 of the pumpkins. Okay, all right. Oh my goodness. One of them actually has their boyfriend with them. Okay, so now there's going to be 4 of us. And I've got to make these mugs of this cake stuff for me and my friends and their boyfriend to enjoy. Okay, so if there's going to be 4 of us, I'm going to mix an S, a spice, and all 3 of my pumpkins. So I'm going to have to make an SP3, a spice pumpkin cake. That's okay, right? I mean, we're gonna mix all those 4 batters together, divide them up into 4 mugs, and everyone's going to have the same cake. Okay, great. Oh, wait, another text? Okay. Oh, now we've got somebody else coming too? Okay, we got 5 of us? All right, so now I'm going to take the mix for a spice, all my pumpkins, and 1 of my devil's food. I don't know if that's going to taste good, but I mean, that's really all I have to do. So I'm going to take the spice cake, the 3 pumpkins, and the devil's food, and I'm going to mix all those batters together and divide it up into the 5 mugs and microwave it, and we're going to have a great treat. Wait, another person's coming? 6 of us? There's going to be 6 of us. Okay, so I'm going to grab the spice and 3 pumpkins and 2 of the devil's food. Okay, now I've got 6 people's worth of batter, and I can divide up into 6 mugs, and then we'll all have delicious cake. So you see how silly that story is, but that's really what the molecule is trying to do. It's trying to make equivalent orbitals for as many electron groups as it needs. So whether it has just 2 electron groups that are linear, 3 that are trigonal planar, 4 that are tetrahedral, 5 that are trigonal bipyramidal, or 6 that are octahedral, it's going to actually mix together the orbitals characteristics and create brand new orbitals, either 2, 3, 4, 5, or 6 of them, whatever it needs, so that everybody gets an equivalent orbital. Okay, so silly story about cake, but I think you understand it's not going to give some groups S's and some groups P's and some groups D's. It's going to make some sort of equivalent same orbital for everybody that has some characteristics of S and P and whatever. Okay, so what I've done just to help you remember that, in addition to having it written down here at the bottom of the front of the page in this section about determining the hybridization, I also went ahead and added this information here in your printout, and so it'll say hybridization if you've got 2 groups is sp3 is sp2, etc. Okay, so that's the idea. So what we're going to do as we work through these problems about the polarity of the molecule, we're also going to specify what the hybridization is about that central atom. And this is something important for you to know, especially going into, say, for example, organic chemistry. The sp, sp2, and sp3 are really common hybridizations for carbon, which is the backbone of organic chemistry. Okay, so the first problem that we said we were going to do is 48. So let me pull out my little textbook here, and let's see what problem 48 is. Okay, problem 48 talks about a molecule of CH3F. And it says this is polar. So they're telling us it's polar, even though it has the tetrahedral geometry that will often lead to a nonpolar molecule. Explain what is going on here with CH3F. So the first thing I want to do is I would like to draw the Lewis structure and kind of see like what's going on here, and then think about the geometry. So carbon, I've got 4 electrons. Hydrogen, I've got 3. Fluorine, I've got 7. I'm going to put the carbon in the middle. I'm going to put the hydrogens and the fluorines around the carbon. So that's going to, let's see, of my 14 electrons, that's going to use up 2, 4, 6, 8. So now I've got 6 electrons left. Again, they go on the terminal atoms first, so 2, 4, 6. Oh, they're all used up. Fluorine's got an octet, carbon's got an octet. Each of the hydrogens has a duet. Okay, so this is what this particular molecule looks like. So if I were to think about the tetrahedral geometry, I'm going to pull off some of these colored balls. Okay, let's imagine these gray ones just have hydrogen, and that this one's the fluorine, this green one. Okay, so it wants us to explain why this is polar, even though often you can get something nonpolar from tetrahedral. So here's the deal. We've only got one bond, right? And as we talked about in the POGL, if there's only one bond, there's no way to kind of balance it on the other side. In order for it to be nonpolar, you would have to have this kind of a bond on the opposite side, or evenly distributed about the central atom. So if I were able to put that sort of bond, oh no, I think I've lost one of my fluorines. Here we go. If I was to put that sort of bond on all 4, then it would be nonpolar. But in this case, there's going to be a separation of charge where the electrons are going to be pulled more toward the fluorine. So this side's going to be more negative, and then this whole side of the molecule is going to be more positive. Okay, so that's how I would explain that for somebody for question 48. For question 50, it says, determine whether each of the molecules from exercise 36 was polar or nonpolar. Okay, so if we look back at question 36, question 36 had CF4. So that's the one that I just built, right? So that would look like a carbon in the center, the fluorines on the outside. If you add up the electrons, they'll be just enough to fill the octet for all the fluorines. And because each of these bonds is polar but it's symmetrical, this is going to be a nonpolar molecule. If we want to talk about the hybridization, which was our other topic for this video, this has 4 regions. I would say this carbon is an sp3 hybridized orbitals that it's trying to use to bond. All right, the next one we have is NF3. And you would put the nitrogen in the center, the fluorines around it. Nitrogen had 5 electrons. We have 21 from the 3 fluorines, so we have 26. I've used up 2, 4, 6. I've got 20 left. So I'm going to start putting them around the fluorines evenly. And now I've used up, of these 20, I've used up 18. So I've got 2 electrons left. That goes on the central atom. Okay? So this molecule if we pretend the black is the nitrogen and the greens are the fluorine, would look like this. So there's a lone pair, and then there's 3 of these nitrogen-fluorine bonds. So if the nitrogen-fluorine bond is polar, and if we look at the difference in electronegativity, it's 1, it is polar, then this side of the molecule with the fluorines would have more electrons than the other side. So this is going to be a polar molecule because we don't have that symmetry of that 4th one pulling there. This one also has 4, so if I was asked the hybridization about this nitrogen atom, I would say it was sp3. All right, going back to 36, our next one is OF2. So oxygen's going to give us 6, the 2 fluorines are going to give us 14. That's going to give us 20 electrons. The oxygen goes in the middle, the fluorines go on the side. We use up 4 electrons. We've got 16 left. So I would start putting them around the fluorines. So 2, 4, 6, 8, 10, 12. When I use up 12, I've got 4 left that go on the central atom. Okay, so this is going to be a case, let's pretend now that the oxygen is the black and the fluorines are the green. We have 2 lone pairs on this tetrahedral basic electronic shape, giving us a bent at probably just a little less really than 109.5 for the molecular geometry. So this guy, because these bonds are polar, is going to go ahead and be polar, more negative toward the fluorine side. So yeah, I would say this one is polar. This one also has 4 electron groups, so it would also be an sp3 hybridization. And then the last one that we have for number 36 is a H2S. So the H2S is going to have 2 electrons from the hydrogen, 6 from the sulfur, so 8 total. We use up 4 in doing the bonds. So we end up with a very similar sort of structure to the previous one, something like this, except for this time we could pretend this is the S and these are the H's, okay? Again, it's going to be tetrahedral electron geometry, bent about 109, molecule geometry, polar bonds, because the difference between H and S is kind of right on the border, but if we're going to say that they're polar bonds, then it would be a polar molecule. If it's not polar bonds, it would not be a polar molecule. And this one would have the same sp3 hybridization. All right, so that takes care of number 50. Let's check out 52. All right, so 52 says, determine the polarity, and we're also going to determine the hybridization of each of these guys. So SiCl4, C, F2Cl2, Se, F6, and IF5. Okay. So let's go ahead and let's sketch out. Now, if you remember, silicon's in the same family as carbon. It's got 4 valence electrons, plus we have 7 times 4, so 28 from the chlorine, so that gives us 32 electrons to work with. We're going to put the silicon in the middle, bond the chlorines 1 on each side. That's going to use up 2, 4, 6, 8 of our electrons, leaving us with 24. We're going to start putting electrons around the chlorines evenly. So now they've all got 2. That one's a little hard to draw, but we've all got 3. So that's going to use up all 24. So this is going to be our structure, okay? So even if these silicon-chlorine bonds are polar, there's going to be symmetry because there's no lone pairs. So again, if we imagine in this case now the silicon is the black one, the chlorines are the green, it's this sort of tetrahedral geometry, both electron and molecule-wise. This one is definitely going to be a non-polar molecule because even if they're polar bonds, we have symmetry. And this one again has 4 groups around it, so its hybridization is sp3. Okay, CF2Cl2, this is going to have the fluorines and the chlorines around the carbon. The carbon has 4. Each of these has 7. So 7 times 4 is 28. We're going to have 32 electrons. We use up 2, 4, 6, 8, leaving us with 24. I'd put them around the fluorines first, so that's going to use up 12, and then the chlorines. That's going to use up another 12. So now we've used up all the electrons, no lone pairs on that carbon, which is good because carbon being in this second row cannot expand its octet to have more than an octet anyway. So this particular one, when I look at the differences in electron negativity, the carbon and the chlorine are about 0.5, but the carbon and the fluorine are a huge difference, 1.5. So we're definitely going to have a stronger pull of electrons over here by the fluorine and less over here by the chlorine. So this is going to be a polar molecule. There's symmetry, but they're not the same strength of polarity. These ones, let's say these are where the fluorines are and these are where the chlorines are. These fluorine ones are much more electronegative. These would definitely be a much more polar side of this particular molecule. Again, we have 4 groups, so it would be sp3 hybridized. All right, let's do SeF6. So Se is in the group with oxygen, so he's going to have 6 electrons. Fluorine, 7 times 6 is 42. We've got 48 electrons. So we're going to put the Se in the middle. Now I'm going to go ahead and bond all of the fluorines to it because Se is down here in the 3rd row. He can expand his octet. So I'm just going to try to draw them, just kind of evenly around here. So 1, 2, 3, 4, 5, 6. Okay, so 6 times 2, we will have used up 12 of our electrons in the bonds. We have 36 more. And with these 6 fluorines, they're all going to want to fill their octets. They're all going to want the electrons evenly. And so luckily, I have 6 times 6. I have just enough to fill all of their octets. So I could go ahead and just draw them in. So 2, 4, 6, 8, 12, 18, 24. There we go. So all 36 and none left over. So this particular one is going to have 6 things bonded to the central atom. So that's going to be octahedral. There's no lone pairs, so the molecule geometry is also octahedral. Even if, and likely it is, this SeF bond is polar, it has symmetry around this whole thing with these bonds that may be polar. So this is definitely going to be a nonpolar molecule. Because it needs to bond 6 things, think about when I had 6 of us to make cakes for. I only have 1 s orbital in any level, so I'm going to use that s first. I only have 3 p's, so I'm going to use up all of those. That gives me 4 equivalent orbitals. I still need 2 more, so now I'm going to have to pull from my devil's food or my d orbitals. So sp3d would be the hybridization. All right, and then the next one that we have is IF5. So iodide is a halogen. He's got 7. Fluorine is also a halogen. So that's 35. So that would be 42 electrons. So I'm going to put the iodide in the middle. I don't tend to like to put a halogen in the middle, but he's one of those ones that can expand his octet, whereas fluorine cannot. And so generally, because he's listed first, he would be less electronegative as well. I'm going to go ahead and put him in the center with the fluorines around. So 2, 4, 6, 8, 10 electrons are being used up. I have 32 left. So I'm going to go ahead and start filling the fluorines valence with octets. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So I've used up 30. I've got 2 electrons left. Now, once you've made all the terminal atoms have an octet, then you're going to go ahead and these last 2 electrons you're going to put on the central atom. And make sure that you draw them in a way that you can kind of see where they are. Okay? So this particular molecule, the IF bonds have a difference in electronegativity of 1.5, so definitely polar bonds. And if I think about something that has 6 around it, right, the electron geometry is octahedral, but one of those being a lone pair, it looks like a square pyramid. as far as the molecular geometry. So this is not going to be symmetric, because notice that this fluorine doesn't have another one here balancing it. So this side is going to be more drawn with the electrons, more negative. So this is going to be a polar molecule. Again, though, because he has 6 around it, he is going to have that hybridization of sp3d2 to give us 6 equivalent orbitals. All right.